Okay, so we do have some experience looking at position and velocity graphs. We're going to go into a little more detail with these right now. You should recognize this position and time linear relationship and how that would be transformed into this velocity time relationship. Okay, so if we found the slope of this line, it looks a little bit greater than 5 meters per second. Okay, that's the velocity that's given here, and if we found the slope, it would match that. This graph shows an object with a displacement west of the origin. As time goes on, the object is moving closer to the origin, so the westward position is decreasing. The slope is negative. It's moving towards the origin, which is east. We usually consider east to be positive. If we transform the position versus time graph into a velocity versus time graph, and we would take that negative slope, meaning constant velocity going east, and on this graph, we would just sketch the velocity going east and give a straight horizontal line for constant velocity. Non-uniform motion is when you change direction or you change your speed or some combination of both of those. An example would be if you're driving your car at 50 miles an hour and you keep your speed at 50 miles an hour, but you take a turn. So your speedometer says 50 miles an hour, but you're turning. So because you're changing direction, that is non-uniform motion. If you were driving along a straight road and you kept speeding up or slowing down, that would be non-uniform motion. And then if you did some combination of speeding up and slowing down while turning, that would be non-uniform motion. Now, as an example, if you were to get in your car, start at 0 and step on the gas, then sometime later you'd be doing 5 miles an hour, and then after that, 15, 20, 30, so on. So that's an example of accelerating. So if we were to plot those data points for position versus time, what we would get is a line curving upward. Now, if we wanted the instantaneous velocity at a particular moment in time, then what we would have to do is draw a tangent line to the curve at that particular time. Find the slope of the tangent line, and that would be the instantaneous velocity at that moment. This is a way of doing calculus with a graph. Now, if we were to take the change in position over the change in time, but we were to add a limit function to the change in time, so the limit would be as time approaches 0, and if we were to do some calculus and integrate that, then what we'd get is the instantaneous velocity at that moment. Okay, so in this situation right here, we have a line curving up for position. So this is showing us acceleration, right? It's not linear. So what they're asking you to do right here is to draw 2 tangent lines, one at 2 seconds and one at 6 seconds. So I'm just going to kind of show you how I would do that. So I'm going to have this red line right here. That's what I'm going to use for the 2 seconds, and then the blue line I'll use for 6 seconds. So basically, move it over here. If this was a piece of paper, and I could just take a ruler, I would take the ruler and I would try to line it up to get tangent on that data point at 2 seconds. But, doing this on screen, kind of have to move things around a little bit. So basically, what I'm doing is I just want my tangent line by definition, is supposed to touch a curve at only one point on the curve. Okay, so like if it was a circle, it would touch it at one point. So in this case, I'm moving it around and I'm eyeballing it. To kind of make it a little easier, I can enlarge or zoom in on the screen here. So I'm looking at my line, okay? It's definitely not touching it at one point. In fact, it's hitting over here, so I need to lower the other end. Let's bring it down here to help out a little bit. Okay. Lower this again. And it's getting very close to where I would want it. And just one more adjustment should do it. Okay. So I think that's pretty good as far as, using this tool here to get it to touch at one point. Okay, and you can kind of see, all right, here's my tangent line, and basically that's where it's contacting the curve. Maybe a little too close right there, but I think this is good enough for what we need to do. Okay, so we're going to do the same thing with this blue line, and when we do that, this is what we end up getting. Again, we'll zoom in on it. Okay, so you can see there's the blue line touching it, and there's the red line touching at 2 seconds. All right, those are my two tangent lines. All right, for those lines, what I would want is I'd want to know some data as far as finding the slope. Okay, so what I'm going to do is I need to get some data points. When you have your tangent lines, the next step is to pick two random points on the line in order to find the slope. So in this case, the points that I'm picking, I'm trying to pick them so at least it's a little easier to get the data. So it happens that the red line crosses here at 6 seconds and 20 meters. So that's a good data point. This other one right here hits at, so that goes up by 10, so it hits at 10 meters, and it just so happens it's right in the middle of 3 to 4 seconds. So that's 3.5 seconds. So that makes life a little easier. So I'm going to type that in. So I'm just going to take this. I'm going to do the same thing, but I'm going to do it for the blue points. So I'm just duplicating that again, just to save time in the editing and typing of all this stuff. So I'm going to make all this blue. So we know that this deals with the blue line. So the X final in this case we decided was 7.4 seconds, and the Y final is 50. Okay, now let's duplicate this again. So this happens to fall on 3 seconds, which is nice and neat. And the distance is 0, also nice and neat. Okay. Fit screen. All right, so now that I have my Y final, Y initial, X final, X initial for each line, I could solve for the slopes. Okay. There are my answers for the two slopes, and what these indicate are the instantaneous velocities at 2 seconds and 6 seconds. Okay. Okay, so check your understanding. Here's an example of a curved line. This is a golf ball rolling along a straight through, which slopes downward from east to west. Okay, so that's the direction it's going, and it's going downward. They give you a tangent line at 3 seconds. Describe the motion, calculate the instantaneous velocity at 3 seconds, and then determine the average velocity between 3 and 6 seconds. So at 0 seconds, the slope is 0 right there. Then the slope is becoming negative. It's going down. So the velocity starts at 0, but then increases in magnitude in the negative direction, which is the west direction. If we're talking about east and west on the compass, east on the x-axis would be positive, west would be negative. Same thing for north and south. North would be positive, south would be negative. So starts at a position east of the reference point of the origin, and then moves westward, arriving at the origin 6 seconds later. So if 0 is the origin, 6 seconds later, it has arrived at the origin. Okay, so that's how you would basically describe this motion. The instantaneous velocity, we would need the slope at 3 seconds. So we could pick different points off this line to calculate the slope. This one's convenient over here. At 8 seconds, it's 0. And then the other one that was chosen was looks like about 24, since these go up by 5. So 24 for the y and 0 for the x. Okay, so that would be the initial y, 24, the initial x, 0, and then the final y is 0, and the final x is 8. Change in y over change in x is the slope, which is change in position over change in time. That's the units you're going to get, meters per second. So when we do this out, it will come out as negative, which is what we want, is a negative slope. Comes out to negative 3 meters per second going east. Now, negative 3 east is really saying 3 west. It's a little confusing. Probably just easier just to say 3 meters per second west, or negative 3 meters per second. The equation for average velocity is the change in time, displacement over the change in time for that particular time interval. So the time interval that they're talking about is from 3 to 6 seconds. So the final time is 6, the initial time is 3. So we need to know the final position minus the initial position at those times. So at 6 seconds, we have position 0, and at 3 seconds, the position was 15. When we look at the chart right here, okay, 3 seconds is 15. So 0 minus 15 divided by 6 minus 3 gives us an average velocity of 5 meters per second west. So during that time interval, that's the average velocity compared to the instantaneous velocity at 3 seconds. And that makes sense. You can see that the slope would be increasing over here. Okay, it's getting steeper.